So what did we do last time? Well, we actually looked into, as you know, that's kind of we do in the lecture, we look at data that can be nested, and we look at data that can be heterogeneous in the sense that the types might not be the same everywhere. You might have a collection of JSON objects that are not exactly the same everywhere. So I give an example like that. Like this is an example of collection where there are 3 objects in that case, but of course, in total, you can have millions or billions of them. And the difference with a relational database, that would be a collection of rows, is that the objects might not be exactly homogeneous. You see there's a bit of a difference between the objects. And what you gain here is a flexibility, because you choose if you want a schema or not. If you don't want any schema, that's fine. You can drop billions of objects and you don't even care what they look like. Or you can have a schema and then all your objects can look the same. What's more, you can first populate the collection with objects and then worry about schema validation after populating. That's the other difference, right? And so what I also said, so this is one dimension that separates between SQL and NoSQL, right? So this is the NoSQL approach. And another dimension that is completely different because it's really independent is whether you first populate your data with ETLE, so you first import your data into the database, or you drop your data on a data lake, S3, HDFS, your local hard drive, and so on, and you just query it from where it is, right? So this is the case with Spark, MapReduce, you know, the Pandas library in Python, and so on. So this is in situ querying versus the good old database way that you first import your data. What is the advantage of that side? Well, it's that here you can actually store your data in an optimized format. And usually this sort of database is much faster. And you can also update your data more easily. Here, this is more for reading the data, but modifying the data is more challenging, even though there are people researching that and things are a bit evolving on that side. All right. So I showed you this query language of MongoDB last time. As you can see, it's not SQL, right? SQL is kind of more convenient, so I have the equivalent here. And you can see that the language here is, it actually uses JavaScript, its function calls, and then you pass kind of queries as JSON objects and so on and so on. The reason why we are paying this cost of a more cumbersome language and a bit lower level is that we now can handle nested and heterogeneous data sets in a way that is very fast. So this is why this API was designed as a subset of SQL. It cannot do joins and so on, but it's incredibly fast. It's like 2 milliseconds answer time typically for a query if it's, for example, a lookup with an index, as we will see. And again, I keep repeating, we will learn that language. Of course, it's part of the lecture, but there will be a better language that we'll discover in the next part of the course. So do not worry. This is, I really wanted to show you, like, these were the early days of document stores where people came up with these languages. And then in the next part of the lecture, we'll have a language that is as high level as SQL. Right? Do we have news? Are they coming?
Yeah, they're coming at 11.
Awesome. Yeah. So we have technical support at 11 for the Zoom integration. Wonderful. Okay. And so what I ended with last time is that I showed you a possible confusion that here, if you submit as a query an actual JSON structure, like name, then a nested object with first associated with Albert, be very careful because that actually looks for an exact match of the object. So this is going to be okay. This not because there is first Albert. That might be confusing because it might not be what you expect. And do you remember, if you also want to return this, what you should do in the query? Anybody? With the dot, exactly. You need to have a dot, so name dot first Albert, and then this will also return this one. And again, it's hard to remember because you cannot guess that, right? The only way you know is you read the documentation and you figure it out. And yeah, so we have to live with that. Okay, so you see how we handle nestedness now is that if you look for special relativity as a theory, so theory is special relativity, it will also accept the case where theories is in fact an array of strings and find one match in the array, right? So this query kind of expands to checking the content of an array. This will be returned. This will not, because there is nowhere special relativity in there. Again, this is low level. The only way you know that it does that is by reading the documentation, but it can do that sort of things, right? Something else you can do is, if you want to, for example, look for specific values in there, but you want to allow multiple values, then you can use this dollar operator. So you remember that the dollar is special, and you can say that the value for university is one of these. So it's dollar in that array. So it's either ETH Zurich or EPFL. So this is why this is going to be accepted, and this not, because it's neither ETH Zurich nor EPFL right there. Okay, everything clear? Right? Do not let yourself be confused by the complexity of the language, because that's pretty much my point, that I want you to see that it's actually a complex and low-level language. All right, nin is not in, it's the opposite. So it's going to look for a value of university that is neither ETH Zurich nor EPFL. So this is not going to be returned, and this is going to be returned. All right. Okay, so then, so we looked at what there is inside this, this JSON object that you can submit to the find function. Now, you can do other things. For example, once you have a query like this that selects a few documents from the collection, you can use .count. That's a JavaScript function called .count. Is going to return to you the count of what you have returned here. That should kind of remind you of a Spark action, right? In Spark, that would be an action, and that's also optimized a bit that it's actually very fast. Okay. What else do we have? We can also sort the output. So for example, if you want to sort by the foundation year, found it, 1 is for increasing, -1 is for decreasing, right? So here we sort by this field, found it in a decreasing fashion. So first, the recently founded universities, and then we go to the older and older and older ones. Okay. And then you have skip and limit. It's pretty much what you have in SQL, right? You have order by, offset, limit. Remember that in SQL? That's for pagination. You can skip the first 30 results, directly jump to the 31st one, and then take the next step. Okay? So this is all the sort of things that you can do. And again, I repeat myself, that is not as easy and straightforward as SQL, because again, that's a lot of parentheses, that's a lot of arbitrary conventions like -1 for decreasing. So it's really a low-level API in JavaScript. Okay, you can also detect the distinct values of a field with distinct last. And finally, you can also have more complex pipelines, where here what's happening, we look for century being 20. We group by year and we group by year and then count to the sum of the count field. We sort increasingly by count, and we limit to 5. Now, this is very low level, but what does that remind you of, this sort of pipeline? SQL, yes, you could absolutely write an equivalent SQL query. And in terms, so yes, absolutely, I see it on Zoom as well. SQL, you had the same idea. And in terms of what it does, yes, that's pretty much SQL. What about the look and feel of the, this pipeline of this and this and this and this? What other technology does it remind you of? On Zoom? I need the SQL answer. Okay, well, it should remind you of Spark, right? That's basically a series of Spark transformations, if you want, right? That's a filter transformation, then that's a grouping transformation, then that's an order by transformation, then this is a take action. It's pretty much Spark, right? So that's it. And here, that would be a creation of getting the collection. So in a way, what happened in MongoDB when they exposed this aggregation pipeline, it's kind of a mini Spark, right? So that's the reason why I'm actually not going to tell you much more about this, apart that it's just like Spark in essence, right? And that's pretty much it. So you see that once you have learned how things work in MapReduce and Spark in terms of how you transform the data And it's like a pipeline, really, of data, and it goes through the transformations. Then you will see that there are many technologies that work pretty much in exactly the same way, right? So this is why I'm not even going in there. You can actually simulate Spark pipelines in that way. And of course, it's going to use the same sorts of technologies in the background. Yes? Yeah, do we have the microphone, by the way, if you want to? I don't think there are any microphones. Oh yeah, I can repeat, or otherwise I can repeat. So the question is, does it make sense also to use Spark if we don't have a cluster of machines, but a single machine? And the answer is absolutely yes. The answer is absolutely yes. If we have a single machine, how can you parallelize? You have cores, exactly, and that's the trick. You can still parallelize across cores. So you can still execute your transformations in a way we would do it on a cluster, but you do it across cores. The only thing that you couldn't do is the I/O of the disk, right? Because there is still one disk on your machine. That's the thing. But you can absolutely use Spark itself also. You can install on your own machine and use in parallel on the core. In fact, on exam day, we will have PySpark and data frames, and you will actually be running Spark on your exam computer. And that's not going to be a cluster of machines. It's just going to be a single computer, right? I can give you the use case. If you are a small company, like a startup, you want some flexibility and some agility in the way you manage your data, because your data schema might actually evolve, right? You need to be able to update your software and your website very quickly because you're still building a prototype. And in a document store like MongoDB, since you don't have to define your schema in advance and you can just change it as you go and keep adding objects that have new fields, it gives you that flexibility. If you use a relational database, it can be tougher because every time you need to modify your schema, you need to migrate a lot of things. You need to migrate your code. You need to, it's very cumbersome. That's the first reason. The second reason is the scaling. Is that if at some point you start having users, you want, by the push of a button, the ability to expand your computing capacity. With a technology like MongoDB, but it's also the same with Spark and others, you can just keep adding more and more and more machines in order to support the workload. That's what the cloud actually gives you. So that's the second use case. And the third use case that then would be in comparison to Spark is that in Spark, you cannot update your data so easily, right? You can query data that is there, that is on S3 or on HDFS. However, you cannot update it. In MongoDB, you can update it. I will show you there are comments for that. And updates are very efficient. That's because it's an ETL system and it's not a data lake system. So you can absolutely update your data in place, modify it, just like you would in a relational database, right? So it's kind of in between Spark and a relational database, a document store, right? Did I answer your question? All right, do we have another question on Zoom?
Yes, so the question is, Spark seems slow compared to PostgreSQL.
Absolutely. You are absolutely right that Spark is slow compared to PostgreSQL. And the reason is exactly this, is that Spark is a data lake. So the data is stored in there. And whenever you need to do something with the data, you need to have all these executors and you need to scan the whole data. This is in contrast with PostgreSQL, that is a relational database. It has index structure. It has a very efficient proprietary format, which means that whenever you want to query data, it can answer like in just a few milliseconds, you get an answer. It's really because the architecture is completely different. Right? There is one way to refer to the difference is that we call OLTP for PostgreSQL, for online transaction processing, because it's the idea that it's transaction intensive, PostgreSQL, as opposed to OLAP, online analytical processing, which is more the Spark side, And the pattern for OLAP is that you really scan the data. And so here it can really be a few minutes, a few hours, or even a few days to scan the data on the data lake, right? But it's very good to really have this, it's this slide that I showed earlier. Let me show you again. It's really about this, right? They are really the OLTP, the online transaction processing. They are very fast. You can update your data, and there are the data lake systems on the other hand, where you really need to scan the data. And of course, these systems are much slower, and these systems are faster, right? Okay. All right. Did I answer your question?
We have another question. Since we need to load the data with MongoDB before we query, how large data sets can we expect to load?
So since we need to load the data with MongoDB, so it's more challenging. I think you need to mute. Yeah, thanks. It's more challenging to import your data in a system like PostgreSQL or like MongoDB, because in a data lake, all you need to do is just drop your data, and you even have tools to copy the data in parallel very easily. In a system like MongoDB, what happens is that your data might be as JSON files or something, and then you have command line tools. So you can import some file that has plenty of JSON objects, and you can pour it into the MongoDB database. Likewise, in SQL, you can have import scripts in SQL, or you can import from CSV and so on, and then you import the data. Importing the data in MongoDB or PostgreSQL takes time, because it really needs to convert everything to the proprietary format and so on. And in fact, here, this is where the data lakes shine, because they don't have this load time that the traditional systems have. So it's really a balance here to find. So typically, if you just want to query your data just once and get insights, then a data lake is better, because you don't have to import your data. If, however, you are going to be reusing the same data set over and over and over and over again and keep querying it, then it might make sense to have a system where you can import your data, because it takes time to import it. But once you have imported it, then things are going to be faster. Did that answer your question? Yeah, awesome. And did it also answer the previous question? What I would say, okay, that's also yes. Wonderful. Okay. So, okay. And now that's what I promised to you. Since we don't have a data lake, but instead we have this importing system, so just like PostgreSQL or a relational database, we have these additional functions that we do not have in Spark or MapReduce. We can insert a document in a collection. We can update documents. We can say, okay, where the last name is Einstein, set the century to 20. And you can delete documents, right? We don't have that in Spark or MapReduce, but we had that in PostgreSQL. So in that sense, MongoDB is like PostgreSQL. In SQL, you also have, right, insert, delete, update. This is something you have in SQL as well. But the syntax here still uses this JSON object syntax for doing so. Okay, any questions so far? All good? So these are the updating capabilities. Now, in terms of atomicity, you can, of course, concurrently modify the system, but you can only modify, get a lock on one document, meaning that there cannot be two people modifying the same document at the same time. Alice might be modifying that document, and Bob might be modifying that document. But for a single document, it's only one person at a time. So if I'm currently modifying that document, anybody else has to wait until I'm done, right? Then, yeah. So then the next step, and this is kind of the transition to what's going to happen the week we start today and finish next week, is that there are better ways to query than what I showed you. This is very low level in JavaScript. I don't know if it scared you, but you know that you can be scared by a language like that, because how are you going to learn all of these details and so on? You keep looking at the documentation. There are languages that allow you to do it at a higher level, fortunately, and then it is more like SQL. They are very easy to learn. And in the next lecture, we look at JSONing, but actually there are plenty of others on the market that basically do like SQL. All right, just 1 minute, please. Yeah, go ahead.
The question is, I don't really see a benefit of using Spark compared to MongoDB.
Yeah, so the main benefit is that in Spark, you don't need to import your data. So you don't have to go through the import process and wait until your data is imported. That would be the main benefit, the first main benefit. The second main benefit of Spark over MongoDB is the scalability. Is that the amount of data you can query with Spark goes beyond what you can do with MongoDB. So MongoDB has improved. It used to be that the typical setup was like with 5 machines or so. They have improved the scalability, but with Spark you can really scale to petabytes of data on an extremely large cluster, much more than you can do with MongoDB. Right. So these are two main advantages of Spark compared to MongoDB. What's very important is that there is no single winner. That really depends on your use case. There are use cases in which Spark will be better, and there are use cases in which MongoDB will be better. Right? Yes?
So when you say you don't pick up the data, so Spark, you mean like you exactly directly read from the Parquet file?
Yeah.
How does like
yeah. So I will come back to the question on Zoom. I had a question in the room too. So the question is that how does it look like when you read? So in Spark, you said you read from Parquet, right, directly from the data lake, and MongoDB. MongoDB has a proprietary format that is called BSON, right? That's what I explained. It's a binary format for JSON, and all of its data is stored in that way. And what's going to happen is that if you have your data in Parquet or JSON or whatever, you cannot read it directly from MongoDB. You first have to use an import tool in order to get that data into MongoDB and convert it to BSON internally. And you cannot just drop your BSON. You really have to let MongoDB take care of it, right? So it's really not like a data lake. Did that answer your question? Yeah, awesome. And then on Zoom.
So the continuous question is, but generally we already had this data stored somewhere in the company.
Yeah, that's actually an argument for Spark too. That's a good argument for Spark. Because in Spark, a lot of people have data on S3, for example, because S3 can be actually used by many systems, not just Spark, but plenty of other systems. So if your data is on S3, using Spark is straightforward, right? But not MongoDB, because you would need to first import your data into MongoDB from S3, right? Is it the meaning of your question?
So do we continue with another one?
Yes, this question I saw the question on the storing the data in MongoDB. I will come to that actually in a few slides on the replicas and multiple machines. Yeah. All right. Yeah. Mr. Abschutz, did it answer your question earlier on the data? Oh, the data set needs to be created somewhere. Yes, absolutely. It can be downloaded from the internet. It can be accumulated via logs. And then when you create the data, of course, you can choose where you store it. So you could store your data on S3 as a log, or you can write it into a database. So when you create the data, you could also directly create it to MongoDB, right? But then again, when you need to move the data, this is where you have extra workload. Right. Or a database of this, you mean a database or a database of data sets, do you mean? Like a catalog. Okay, let's take it offline. You can write us on Mattermost, and then I'll make sure that that I can answer this question. All right. So a few words now on the architecture. So you remember what we learned on Spark and MapReduce? We love to shard the data. We cut the collection in partitions and we just shard the data. We love to replicate the data. If we can store it multiple times, then there is less risk that we are going to lose data. And finally, we like to store the data on plenty of different machines because this is how we actually scale out, right? So these are the three principles. We have them in Spark, and it turns out that we also have that in MongoDB because in a document store, we have these collections and we can absolutely replicate the collection multiple times and shard the collection, right? So we both replicate, that's the vertical dimension, and shard, that's the horizontal dimension. In MongoDB, they call a shard a replica set. It's the machine that should store the shards that they call replica set. So you have a replica set, and maybe the replica set is going to handle F to P, right? For a specific part of your collection, if there is a key somewhere, F to P is in that replica set, A to E is here, and Q to Z is here. So here we have 3 replica sets, and in each replica set, you have several replicas of the same shard. And the idea, the architecture is that you have one machine that is the primary machine, and you have 2 secondary machines that store a copy of the data, right? So you do have this sort of architecture, but it's not a centralized architecture like in Spark, where you had a single master and plenty of workers, right? In that case, it's really per replica set, there is a primary machine and secondary machines. So now if you have multiple shards, there will be 1 replica set here, 1 replica set here, 1 replica set here. So you see, it's not the same architecture as Spark. And the idea is that this is for every shard, you have 1 machine to communicate with. You typically do not communicate with the secondary machines, but they still have a copy of the data. So if you want to write data, there is, of course, a central kind of MongoDB server that is responsible for communicating with all the replica sets. But when you write data, what happens is that you have an acknowledgement that is being written here, and then you wait for the acknowledgements for the secondary machines, like acknowledgement, and you can define as a user a minimum of acknowledgements that you need. So if you say, I want at least 3, then that's it. You have a confirmation, and then you can go ahead and do something else. And then later in the background, it will continue to replicate to the other machines, right? So this is a flexibility you do not have with PostgreSQL, right? PostgreSQL guarantees to you the consistency and the durability of your data. Here in MongoDB, you can even say, it's enough that I have 1 acknowledgement here. I don't even want to wait for the other acknowledgement. I'm taking the risk, of course, that exactly after that, there's an electricity issue and these machines crash. But it's up to you as the user, right, to say that. So you can go all the way being super risk-friendly and say, I just need 1 acknowledgement, or extremely paranoid and conservative and saying, I want everybody here to acknowledge that they have a copy of my data. Right. Then it takes longer, but then it's everywhere. Okay, any questions? No? All right, so let's go then to something very important that we have in MongoDB, but we do not have in Spark. And that is also one of the differences. You probably noticed that when you have a book, on the last page of a book, you typically have an alphabetical list of words, right? And when you're looking for a specific topic, you look it up alphabetically, and then you find it, and then it points you to the page. That is an index. And in fact, in PostgreSQL and in MongoDB, we have structures like that are exactly like what you have at the end of a book. So the idea, for example, is that what if I want to easily locate these fruits by the color that they have? Or what if here I have billions of objects, billions of scientists, mathematicians, and I want to retrieve them efficiently by profession, right? Or by name, What if I want to easily find Euler here? It's not even alphabetically sorted, you see? So with Spark, you would do a full scan. With Spark, you can define a filter. You can read the entire data, you can filter it, and then you get that out, but it might take an hour. But with an index, MongoDB, you can actually do that in 2 milliseconds. Likewise, so this is here called a point query because the result is typically just one result. There are also queries that are called not highly filtering, like all the mathematicians, because then it's not going to be just one result, right? You may get 1,000 results out of the million in the collection, right? So point query, right? And here it's not a highly filtering query, right? Then you have range queries. A range query is when you have, for example, numbers or years, and you look for intervals. For example, you say everything that is after 1900, everything that is before 2000, everything that is between 2000 and 2020. This is called a range query. So you need to understand these kind of queries in order to understand how you can optimize them with indices. How can we make this super fast, this sort of queries? And the answer is with an index. And an index works like this. It's a structure that you add on top where it takes time to build, of course. But basically, you have this list of colors, in that case, if you index by color, and every color points directly to the objects that have it. Like yellow, for example, points to banana and ananas, right? And when you want to query something, for example, you want everything that's orange, you look it up in the index. Typically, it's going to be alphabetically sorted in a way you can find it easily. And then you follow the pointer and you directly get that. This takes 2 milliseconds as opposed to an hour with Spark if you wait until this is done, right? All right, so there are 2 kinds of indices that I'm going to show to you, hash indices and tree indices. So I'm going to go in turn with the 2 of them. We still have 5 minutes. So let me explain hash indices. So imagine we have this collection of objects and we would like to index by century, right? We have these centuries right there. And we would like to build a structure that allows us to very easily find the century. Well, the good news is that MongoDB can do it for you. So in MongoDB, you have this magic function called create index that you call on the database scientist, create index, and you say what you want to index on, in that case, the century, and you just say hash. Hash is going to create a hash index. That's what I'm going to show you what it's made of. But this is it. Just this, if you type it in MongoDB, it's going to create the index. Beware, once you have put that in the shell, if you have a very large collection, MongoDB might start working like crazy for an hour because it's building the index, right? So you need to wait until the index is actually built before you can use it. On the other hand, if you build the index on an empty collection because you didn't put your data yet, then that's going to be very fast. But then every time you write a new object in the collection, it's going to be a tiny bit slower because the index needs to be refreshed every time. All right? Okay. So let's build the index together then. This is how it works. We go object by object and we add it to our index. So we take this object here, century 20, and we have, this is the only piece of magic that we have, it's a function h. That's called the hash function. This function is a mathematically magic function. It's actually part of cryptography and these sort of things. It's like really converting whatever you give it as input, can be anything, and it's going to output an integer. That's called the hash function. In that case, that magic function tells me 0. That is the position I will use in this big table that I have right there. So it says 0. So 0, you know, in computer science, we love to start with 0. So it's 0, 1, 2, 3, 4, 5, and so on. So I take 0, I put the 20 in there, and I put a pointer to my record here. Why did I say this function is magic? Because this is instant. When you call that function, you immediately got the result 0. Inside, it's typically addition, multiplication modulo, what's going on there. It's basically cryptographically based. I'm not going into the details of that. There are lectures for that. But it's basically a function that instantly gives me a position in there. So then I take the next one, 20. So of course, this function is deterministic, so it's always going to return the same position for the same input. Then 19, here it returns 4, okay, then position 4. And then I have the pointer, then I have -4. H of -4 is 3, so I put it there. Then I have -6, H gives me 1, so 0, 1, 2, 3, 4, 5, right? Again, that's the position. And 20 gives me 0. Now, the behavior of H is kind of unpredictable as a human. It's just like randomness. So it looks like it just picks a random position, but it's always the same position. That's what's important. Right. So it's a bit of a mess in the way that it's put in there, but H is very fast. So now that I have built my index, of course, there might be also empty cells there, and somebody comes with a query century 19, how can I use my index to answer that query? Exactly, you hash 19. So you take H of 19 gives you 4. So here it's very quick to find position 4. We know how to do that in the computer. So 0, 1, 2, 3, 4. It's instant, we go there and we follow the pointer. You see, that's how we do it in 2 milliseconds. In Spark, we would have had to scan the entire data set. But in MongoDB, we have this index and we just use the magical hash function to directly find the pointer that tells me what object to return. So you have if I have a point query with very few results, this is almost instant. And by the way, PostgreSQL also has that, just like MongoDB. It's something that is actually borrowed from relational databases. All right. I think it's already time for the break. Let's take the time for the break. Then I'll explain to you the other. Do we have one question? Go ahead. Oh, the value record, it's just a tuple. It's called the tuple. This is basically a vector or a list. And then you just have a tuple with the value at the pointer. Of course, we are optimistically assuming there are no collisions, because if you have two values that land in the same position, then we know how to deal with it, but it's extra work. You can consider it as an array, yes, or no. Exactly, if you have collisions, that would be a linked list that you have here. So there is a vector and then a linked list. All right. So, okay. So let's take a break. It's ringing now, and I'll see you in 10 minutes. And we'll see if tech support allows us to have the Zoom integration working. All right. Thank you very much. See you in 10 minutes.